Remember ʻOumuamua? Picture that moment in October 2017 when that elongated visitor from beyond our solar system tumbled through the cosmic neighborhood near Earth at breakneck speed, leaving scientists utterly speechless. Its cigar-like shape spun chaotically between light and shadow, glinting like polished metal. And strangest of all, it accelerated as it moved away from the sun without any tail or gas emissions to explain the thrust. I was among those tracking it in real time, and like many colleagues, I wondered if we were witnessing something beyond the bounds of nature. Harvard astrophysicist Avi Loeb posed a question that rattled the community. What if ʻOumuamua wasn't entirely natural? What if it was technology, a light sail crafted by some civilization to drift on the photons of stars? Back then, most scientists dismissed the idea as wild speculation, but maybe, just maybe, we weren't ready to see what was right in front of us. And now, 8 years later, another visitor has arrived. We call it 3I/ATLS, the third interstellar object ever detected, and the first in history that doesn't reflect light but absorbs it. It doesn't do what ʻOumuamua did, it does the exact opposite. As Atlas approached the sun, telescopes recorded something absurd. Light at the 1.064 micron wavelength, precisely the frequency humans use in industrial laser systems, vanished from its reflection spectrum. No scattering, no interference, just a perfect dark gap, as if the object was devouring light. At the same time, infrared data from James Webb showed ATLS's dark side, emitting steady radiation at 290 Kelvin, regardless of its changing distance from the sun. In physics, this is impossible. No comet or asteroid maintains a stable temperature in the cold vacuum of space. Nature doesn't know how to regulate energy so precisely, but ATLS does. When researchers at JPL rechecked the data, they found the absorption occurred exactly in the spectrum of Jaeger lasers, which humans use to transmit energy in space. A random coincidence or a deliberate response? When the first data came down from James Webb and Hubble, everything seemed normal, just a small object, moving on an orbit cutting across the ecliptic plane, reflecting light faintly but steadily. Then spectroscopists started noticing something wrong. Across the entire spectrum, there was a perfect narrow gap, a white cut where light should have been. Not noise, not dust or shadow. Light at 1.064 microns was truly gone. Independent observatories in Chile, South Africa, and Hawaii all confirmed the same thing. The light was eaten. No scattering, no reflection, no secondary emission, a pure void, as if the object was built to swallow photons at that exact energy band. Scientists at NASA, ESA, and Harvard's Institute for Astrophysics began a flurry of emergency meetings. I was at one in Pasadena. In the dimly lit room, projector light fell on spectral graphs, their curves quietly dropping into a blank gap at the center. No one could speak. An optics materials expert whispered, "If this is natural, nature just became an engineer." The next infrared measurements stunned the group. Atlas's dark side emitted steady radiation at 290 Kelvin, equivalent to 16.85 degrees Celsius, unchanging even as it neared the sun by tens of millions of kilometers. No thermal fluctuations, no surface heating, no signs of energy loss. With comets, approaching the sun causes surface ice to vaporize violently, forming a bright tail and clear thermal variations. But Atlas behaved like a device with active thermal regulation, a mechanism keeping its entire surface in constant equilibrium. That's unprecedented. And then there was something else, something that shattered every natural hypothesis. When JPL's Doppler analysis team checked the reflection data, they detected micro-oscillations with a precise 22.4-hour cycle. The variation was only a few meters per second, but consistent and directed. Then a radio observation team at Goldstone detected a faint laser signal, almost lost in background noise, coming from Saturn's direction with the same oscillation phase as Atlas's variations. The coincidence made everyone in the room hold their breath. The signal was emitted, reflected, and returned with a cycle identical to the object's micromotions. Something or someone was sending and receiving signals. Within 48 hours, a joint committee of NASA, ESA, and the Japan Space Agency was formed to cross-check data. They called it the Photon Anomaly Protocol. I vividly recall the faces of the scientists in the conference room, exhilarated yet terrified. We'd spent a century studying how light travels through the cosmos, and now it seemed light was answering us in its own way. I stood before the screen, staring at the spectrum with its 1.064 micron cut and steady oscillations. We thought we understood light, but maybe light understands us. If ʻOumuamua made us suspect something was moving with purpose, Atlas suggests a form of light-based communication beyond imagination. As news of the swallowed 1.064 micron light spread, the global physics community split into two camps. One insisted it was a measurement error or instrument noise. The other, more cautious but resolute, argued we'd witnessed an unknown optical phenomenon. I attended an online workshop with NASA, ESA, and the Max Planck Institute for Physics. On the screen, dozens of scientists stared at a familiar number, 1.064 microns, the standard emission frequency of NDY lasers used everywhere on Earth, from medical surgeries to metal cutting to wireless energy transmission between satellites. To engineers, it's an industrial frequency, a human tool, and now an object from beyond our solar system was absorbing that exact band, not deviating by even 0.001 microns, a statistical coincidence near zero. Physically, a natural object's light reflection follows simple rules: reflection, scattering, absorption. Reflection happens on smooth surfaces, light bounces back. Scattering occurs on rough surfaces, light disperses in many directions. Absorption, as we know it, converts photon energy into heat. But nature doesn't choose. No natural object absorbs a single wavelength while ignoring billions of others. In chemistry, selective absorption involves precisely arranged electron structures, like in deliberately designed materials. In the cosmos, no random process creates an optical structure so finely tuned. An MIT team proposed a surface defect resonance hypothesis that a crystalline structure on Atlas' surface might resonate at exactly 1.064 microns, causing anomalous absorption. But mathematical models showed this was highly unlikely and couldn't explain the 290 K thermal stability. Another team at Cambridge suggested a calibration error in JWST's sensors, a ghost artifact. Yet when ground-based observatories, Mars Orbit telescopes, and Hubble all confirmed the same absorption band, the error hypothesis was nearly ruled out. I recall a CERN researcher saying during the meeting, "If this is an error, the universe just conspired with every telescope at once." The room laughed, but the laughter faded quickly, as no one was sure it was wrong. At JPL, my optics team tried simulating the reflection spectrum from a surface with nanostructured materials like those engineered on Earth. The result was chilling. Only a metasurface designed to block photons in a fixed band produced a graph matching the real data. And such metasurfaces, at least on Earth, exist only in labs for cutting-edge optical tech projects. When I saw the simulated spectrum match Atlas's perfectly, I felt it clearly. This was no longer nature's prank. It was a question sent to humanity in the language of light. Physics institutes in the US and Europe began sharing internal papers. Journals like Nature and Science received a flood of manuscripts with titles like Selective Photon, Absorption of 3I/ATLs, and Non-Thermal Stability in Interstellar Objects. But no one dared publish yet. The reason was simple. No one wanted to be the first to say the universe just did something that seemed intentional. At some level, this is the classic clash between two schools of physics: certainty versus exploration. One wants to believe every phenomenon fits existing models. The other accepts that the universe might operate on principles we've yet to touch. I recall telling a colleague during that meeting, we saw ʻOumuamua change velocity, saw Borisov carry strange chemistry, but Atlas, it doesn't move strangely, it shines strangely. All three objects feel like successive tests. ʻOumuamua challenged mechanics, Borisov challenged chemistry, and ATLs now challenges optics and our intellect. Three visitors, 3 times the universe tossed us a new puzzle piece. And perhaps this third test isn't about motion or gravity anymore, it's about light. When July's final data was confirmed, I knew we'd crossed the line from strange to impossible. Every natural model collapsed, leaving only 3 hypotheses, each a doorway into the deepest mystery of the optical enigma called 3I/ATLs. The first, from Caltech's theoretical optics group, was the metamaterial skin hypothesis. ATL's surface isn't rock, ice, or raw metal like a typical comet, but a sophisticated graphitic lattice of interwoven carbon nanofibers, creating a band-stop effect, the ability to block a single photon frequency precisely. With this mechanism, light at 1.064 microns is completely nullified, like a sound filter removing one note from a symphony. In physics, this is optical stealth technology. Light is captured, absorbed, and slowly re-emitted in another direction, making the object nearly invisible in the usual reflection spectrum. I saw a 3D simulation of this structure, and it truly resembled a photon cloaking device, each lattice cell acting as a nanomirror, controlling light flow with precision only Earth's cutting-edge labs achieve in a few square micrometers. If Atlas is covered in such a structure, it means someone or something crafted a surface designed to avoid detection. The second hypothesis, from an ESA team, was the optical relay system. They asked, what if the 1.064 micron absorption isn't just a material property, but an active process? In this model, Atlas doesn't just absorb light, it collects laser energy from a distant source, possibly near Saturn, where the faint oscillating signal was detected. Photons are taken in, energy stored, and re-emitted as infrared heat, maintaining the steady 290 Kelvin temperature, a perfect energy regulation system. The 22.4-hour cycle, rather than random oscillation, could be the charge-discharge rhythm. In other words, Atlas functions like a cosmic solar cell, not reliant on the sun, but linked to another invisible energy network, silent yet present. I recall saying in an internal interview, if this is true, we just found an interplanetary wireless energy transfer tech, not via radio waves, but pure light. The room fell silent, not from doubt, but from awe at the hypothesis's scale. The third hypothesis, seen by many as the wildest, is the one I couldn't look away from, the photonic grid node. In this model, 3I/ATLS isn't a lone object. It's a component in an interstellar network where energy moves through space via directed photons, a cosmic internet, but instead of data, it transports energy. Each node, like Atlas, absorbs light at a specific frequency, converts it, and re-emits it at another to relay to the next node. If so, Atlas is an ancient relay station, possibly millions of years old, still doing its job, indifferent to who's watching. Picturing this, I thought of my own metaphor. This isn't just a rock in space. It's like a forgotten power station, quietly lighting up the cosmos with energy we're not yet smart enough to recognize. Each hypothesis was tested, simulated, debated, and though they differ in details, they share one thing: they treat Atlas as something built with purpose. No one can confirm it, but no one can prove otherwise either. When discussions become too heavy with hypotheses and too light on evidence, the first thing to vanish from public communication is information. Within a week of the 3I/Atlas data being shared among observatories, all public updates abruptly stopped. NASA's spectral tracking page went into temporary maintenance. Issei's database switched to internal mode. Observations from China's National Astronomical Center ceased publication. To the public, it felt like suspicious silence. But I understood this wasn't concealment, but institutional caution. In science, when a phenomenon outstrips current understanding, the wisest move isn't to proclaim, but to pause and cross-verify. A single sensor glitch, a misprocessed algorithm, one tiny error could spark a storm. So, instead of speaking, they chose silence. At Pasadena, JPL's lab shifted to data quarantine mode. Every spectral file was marked classified, technical review, and accessed only in a radiation-controlled environment. In Geneva, Issei's analysis team halted public data updates and began cross-checking between Webb, Hubble, and ground-based observatories. In Beijing, the Chinese Academy of Sciences joined the International SETI protocol, synchronizing photon analysis standards with the US and Europe. It was the first time since the Voyager program that the three space superpowers collaborated to verify a single signal. I recall an online meeting among the three centers, hundreds of faces on the screen. Everyone spoke in low, slow voices, as if afraid sound itself could distort the data. A strange feeling permeated the room, not fear, but absolute reverence. A colleague of mine said, "When everyone goes quiet, it doesn't mean they're hiding something. Maybe they're just trying not to break something too fragile." I think he was right. The universe just handed us a signal that could rewrite how we understand life and energy, and the world can't afford to react with reckless frenzy. I call this pause the silence of data, not a silence from lack of information, but because we have too much and lack the capacity to interpret it. At some level, it's science's survival instinct when facing the unknown. Humanity steps back, holds its breath, then moves forward. I said on a broadcast something that was widely quoted afterward. When the world goes silent, it's not fear, it's the moment we tread carefully before new light. And I believe it because light, when it speaks the universe's language, always outpaces human intellect by a few generations. Now, as all lenses temporarily turn away from Atlas, I see no shadow of conspiracy or secrecy. I only see thousands of scientists, tense in silence, hands trembling before screens, waiting for one more photon to confirm that the universe truly did the impossible. As late October 2025 approached, the entire astronomy community knew the decisive moment was near. The 3I/Atlas was about to pass perihelion, its closest point to the Sun, from October 29th to 31. In science, we call this phase the universe's test. It's the moment when heat, radiation, and gravity peak, where every natural comet reveals its true nature. If something's anomalous, it'll show now. NASA, ESA, and CNSA activated a global observation plan. 13 optical telescopes were synchronized. 2 satellites, James Webb and JUICE, positioned optimally to track the full light spectrum for 72 hours. I recall a Pasadena engineer's voice over the radio. "This is the first time in history we're aiming lenses at an object that might be interstellar infrastructure." The world held its breath. From a physics perspective, this was the perfect experimental stage. If the 1.064 micron absorption was natural, the sun's radiation storm would disrupt it. But if it was artificial, the structure would hold or even respond deliberately. 3 scenarios were predicted, each research team assigned to monitor one. The first, simplest, and most reassuring was that everything returns to normal. As Atlas nears the sun, its temperature rises, material evaporates, the absorption band vanishes, and the object behaves like a typical comet. The scientific community breathes a sigh of relief. The mystery resolved. It was just a quirk of physics, perhaps a strange carbon surface or a rare plasma effect. The planet would relax as we reclaim stability in our models. The second, riskier scenario is that the absorption band persists, unchanged despite the sun's doubled radiation intensity. If that happens, it means Atlas's surface is structured to withstand high energy without degrading, possible only in artificial materials or actively controlled thermal systems. At that point, alien technology stops being science fiction. In JPL's control room, someone had written on a whiteboard, if the band stays, physics changes. But then there's a third scenario, one that makes everyone shudder to consider. If, during perihelion, Atlas not only retains the absorption band, but amplifies its 22.4-hour oscillation, syncing perfectly with a faint laser signal from Saturn's direction, it would mean the object is exchanging energy or information with another source. A relay station, an optical relay operating between planets. If true, we wouldn't just be observing an object, we'd be witnessing part of a cosmic energy network functioning before our eyes. I said on CNN on October 27th, we're about to look into the mirror of the future, either seeing our own reflection or another civilization looking back. At that moment, no one knew which outcome awaited. Telescopes began tracking 24/7. Data streamed in, each photon measured, recorded, compared. Every hour, screens displayed thousands more spectra. The sun's light blazed, while scientists sat in darkness, waiting for the impossible. I recall telling the control team, if the band vanishes today, we learn about nature. But if it stays, we'll have to relearn the universe. We spent hours watching running graphs. The curves trembled, shifting in tiny increments. Some signals showed the absorption depth slightly increasing, not fading. No one dared say what it meant. No one wanted to conclude too soon. We all understood, one misstep, one wrong measurement, and it all falls apart. But just one photon, one signal in phase, could rewrite the history of physics. As the clock ticked to 0 o'clock on November 1st, perihelion passed. Data was still being processed, but I knew, whatever the outcome, this test had changed us. When the final perihelion data was decoded, I remember sitting for a long time before the screen, staring at spectra as delicate as a breath. No cheers, no collapse, just silence, the silence of those who've touched the edge of knowledge. Whatever the results leaned toward, one thing was clear: the universe might be smarter than we ever imagined. I once said that if there's a language every civilization understands, it's light. Light is the universal signal, needing no translation. Each photon carries information about its source, energy, and intent. Now, looking back at what Atlas did, absorbing, holding heat, oscillating, responding, I'm starting to think we're witnessing an intelligent energy network operating in that very language. Not radio, not digital signals, but a cosmic internet of light. Perhaps, when a civilization reaches a high enough level, they no longer use radio waves or crude signals to communicate. They control energy directly. They speak in photons, in the presence and absence of light. And if that's true, Atlas might just be a node in that vast network, an energy gateway among the stars, where information isn't sent but propagated. I once said in a Columbia lecture, every civilization that masters energy ultimately masters light. Because light isn't just a tool, it's the essence of intelligence. When we control photons, we control how the universe transmits information. To them, sending a precise laser pulse might be simpler than flipping a light switch is for us. And if so, they don't need radio stations or flashy signals to be noticed. They could hide in the universe's light, in what we dismiss as background noise. This brings me back to the Fermi paradox. The classic question, if aliens exist, why haven't we seen them? Maybe the answer is they're everywhere, but hidden in photons. They've merged with the universe's energy flow, becoming part of the light we see every night, part of a glow the naked eye can't discern. And perhaps, because they're so advanced, we're not yet refined enough to realize they're speaking not in words, not in waves, but in the deliberate absence of light. Maybe when we look at Asius, we're not seeing a lone object, but a dot on the universe's energy map, a point where humanity just received its first data packet, as 3I/Asius moved away from perihelion and began its journey outward. Telescopes tracked it until the last faint reflected light hit James Webb's sensors. A fragile streak of light, hovering in the dark, then gone. All that remained was data, terabytes of photons compressed into numbers, meaningless without human intellect to interpret them. I sat in the control room, watching the fading light graph, and thought, maybe this is what science always aims for, not answers, but moments of realization. We learn to measure light to understand the universe, but now I feel like light is measuring us, testing if we're humble enough to see we're still students in the vast cosmic school. 3I/Asius doesn't speak, doesn't signal, doesn't send messages, it just exists, quietly and patiently, as if teaching us the limits of understanding. In every lost photon, there might be a question. In every silent wavelength, a reminder that knowledge isn't a destination, but an endless journey. As a child, I looked up at the sky and wondered why stars shine. Now, after half a century of research, I'm wondering the opposite. Why does some light not shine? That question, simple yet profound, might lead humanity to the next chapter in our quest for knowledge. Because the universe never stops challenging us. It always conjures new phenomena to keep us curious, exploring, and redefining understanding. I believe science's greatest purpose isn't to confirm what we know, but to nurture our capacity for wonder. Each time the universe confounds us, it brings us closer to ourselves. Maybe 3I/ATLS didn't come to deliver a message or prove another civilization's existence. Perhaps it came to ask humanity, are you ready to hear light tell its own story? And if the answer is yes, we've just opened the first door, not just looking outward, but inward, where light for the first time in history becomes humanity's teacher. If you believe the universe still has untold stories in every ray of light, subscribe to the channel to join me on this journey of discovery. Thank you for following. See you in the next video, where we'll listen to what light has to say to humanity.